Good morning, everyone. I'm Xianghao from Nanjing University of Science and Technology. Today it's my honor to present our work, GraphSD, which is an IO-efficient framework for out-of-core graph processing. My presentation includes four parts. First, we introduce the background. Graph has been widely used to express many models in our lives, like web graph, social graph, road network, and biological structure. Many graph algorithms can be used to address the real-world problems. For example, social networks can use community detection to realize the function of friend recommendation. The shortest path algorithm can be used to support the navigation in the road map. As graph processing becomes more and more popular, many graph-specific processing systems appear in recent years. According to the underlying hardware platform, they can be classified into three categories: distributed, shared memory, and out-of-core or disk-based graph processing system. Distributed systems can scale to very large graphs, but they require an expensive cluster and often suffer from the problem of load imbalance and communication overheads. Shared memory systems are easy to deploy, but the capability is limited by the memory capacity of a single machine when handling very large graphs. While for the out-of-core system, many recent works like GraphTree and GridGraph have shown that they can be competitive to distributed systems by efficiently using the secondary storage. Furthermore, they are affordable and easy for users to program. Therefore, they are the most cost-effective solution and attract many attentions in recent years. When handling an input graph, the out-of-core graph processing system first divides the vertex side of the graph into disjoint intervals and the edge side into several smaller partitions. Each partition contains the incoming or outgoing edges of the corresponding vertex interval. During the processing of the graph, the system successively loads and processes each vertex interval and the corresponding edge partition from disk. As the system needs to load the edge partitions from disk many times when running a graph algorithm, the disk I/O overheads naturally become the key performance bottleneck of these systems. Many researchers show disk I/O can contribute to over 70% of the total execution time. Therefore, our target is to reduce the disk I/O overheads as many as possible. Next, we introduce the Manysense of our work, which are stemmed from the following observations. First, existing out-of-core graph processing systems ensure the data access locality by sacrificing the I/O amount. Specifically, they load all graph data in each iteration to realize the sequential data access. However, many graph algorithms only need to access a small portion of graph data. This figure shows the percentage of active edges or useful edges in each iteration for different algorithms. We can see that the number of active edges is very small in most iterations for BFS and WCC. However, many existing works are unaware of the states of vertices during processing. They rapidly load the useless data or inactive data into memory and incur significant I/O inefficiencies. Our aim is to design a state-aware I/O scheduling strategy that can adaptively access a graph data based on the states of vertices or the number of active vertices. If the number of active vertices in the current iteration is small, the system selectively loads the active edges to avoid the unnecessary data accesses. Otherwise, it loads all edges to realize the sequential disk I/O. To enable the system to make a right decision between these two kinds of I/O access model, we implement an efficient performance benefit evaluation model. Specifically, before the execution of each iteration, The system first computes the performance benefit of each I/O model and selects the better one. The performance benefit is estimated based on the I/O cost of each I/O access model. On the other hand, the existing graph algorithms are usually organized in many iterations. The back-synchronous parallel model, or BSP, is the most popular iterative graph processing model. In this parallel model, the value of a vertex in the current iteration is computed based on the values of its neighbors in the previous iteration. In this PageRank example, the rank value of vertex v in iteration t is dependent on the value of each neighbor u in iteration t-1. By such separating of the values being generated and the values being used, the BSP model can ensure the consistency and correctness of algorithm executions. In fact, the dependencies among vertices defined by the BSP model provide an opportunity to proactively compute the vertex values in the future iterations. In this example, the system successfully processes graph partition P0 and P1. In iteration t, after processing P0, the corresponding vertex interval, that is, vertex 1, 2, and 3, are also updated. Therefore, when processing P1, since the values of vertex 1 and 2 are already updated in the current iteration, the system can further use their values to update the values of vertex 4 and 5 in the next iteration. In iteration t plus 1, when processing P1, since the updates from vertex 1 and 2 propagated to vertex 4 and 5 have already been done in iteration t, the corresponding edges need not to be loaded. As a result, the overall I/O traffic is reduced. This is called the future vertex updating or cross-iteration vertex updating. By combining the above two designs, we propose an I/O-efficient out-of-core graph processing system called GraphSD. Its key idea is to simultaneously capture the state and dependency of graph data during computation to significantly reduce I/O traffic. A state and dependency-aware update strategy is proposed to support both active vertex-aware processing and cross-iteration vertex updating. Moreover, we also design an efficient buffering scheme to further reduce I/O costs. In the following, we introduce the detailed designs and implementations of GraphSD. We first present the graph representation of GraphSD. We use the two-dimensional partition method to organize the graph data. Specifically, we first split the vertices of the graph into several intervals like previous work. Then each vertex interval associates an edge block to store the outer edges of the vertices within the interval. Furthermore, each edge block is further divided into several subblocks according to their destination vertices. For example, for edge 1, 5, the source vertex 1 belongs to interval 1, while the destination vertex 5 belongs to interval 2. Therefore, this edge is assigned to subblock 1, 2. Next, we illustrate the execution procedure of the update strategy of GraphSD with the following example. Let's consider two situations. Supposing the active vertices in the current iteration is 1, 3, and 4. GraphSD successively processes from subblock 1, 1 to subblock 2, 2. In this case, since the number of active vertices is small, GraphSD selectively loads the active edges into memory when processing each subblock. After all subblocks are processed, some vertices are activated again and their edges are already loaded into memory. such as vertex 1 and 3 and their edges. Therefore, GraphSD can directly update the neighbors' values of vertex 1 and 3 in the next iteration in advance, and GraphSD needs now to load these edges in the next iteration. When the number of the active vertices is large, GraphSD sequentially loads all edges into memory when processing each subblock. After the vertices in an interval are updated, GraphSD can perform cross-iteration vertex updating to update the vertex values in the next iteration. For instance, after subblock 11 and subblock 21 are processed, the vertex value of interval 1 in iteration t are updated. GraphSD can exploit these newly updated vertices to perform cross-iteration vertex updating. In this example, subblock 11, subblock 12, and subblock 22 can enable cross-iteration vertex updating. While for subblock 21, it cannot support cross-iteration vertex updating, since its source vertices have not been fully updated in the current iteration when processing it. In iteration t plus 1, only subblock 21 is required to be loaded. Obviously, the I/O traffic can be greatly reduced. And the subblocks like subblock 21 are loaded more frequently than other subblocks, since they can now support cross-iteration vertex updating and need to be loaded in all iterations. It provides us an opportunity to further reduce this I/O by buffering these subblocks in DRAM. However, there may not be enough memory to catch all these subblocks, especially for very large graphs. It requires us to design a replacement strategy for the buffered subblocks. Specifically, we judiciously buffer the subblocks based on their priorities. The priority of a subblock is determined by the number of the active edges in this subblock. Therefore, during the processing, the buffered subblock with the lowest priority will be evicted. Now we report our evaluation results. We conduct the experiment on a commodity machine. The testing graph algorithm includes PageRank data, weakly connected components, and single-source shortest path. We compare GraphSD with two state-of-art out-of-core graph processing systems, Hasgraph and Lumos. The testing dataset includes several real-world social networks and web graph, and one syntactic graph. We first evaluate the overall performance. Note that Hasgraph and Lumos can support selective data access and cross-iteration vertex update respectively, while for GraphSD, it simultaneously captures the state and dependency of graph data during the computation. Therefore, they can support both selective data access and cross-iteration vertex updating. Therefore, GraphSD can achieve a 1.7 and 2.7 performance improvement compared with other two systems. We then evaluate the I/O traffic. Compared with other two systems, GraphSD can reduce the whole amount of I/Os by 1.6 and 5.4 times. We also evaluate the effects of different system designs, including the cross-iteration vertex update and the selective vertex update. We evaluate the system performance by disabling each design. From the results, the selective data access and cross-iteration vertex updating can bring about 2.8 and 1.7 of performance gains. We then evaluate the effects of different I/O access models. We compare GraphSD with two baseline systems that use the full I/O model and the on-demand I/O model in each iteration respectively. We can see that GraphSD is able to select the optimal I/O access model in each iteration, thanks to the state-aware I/O scheduling strategy. In conclusion, the existing out-of-core graph processing system have not fully exploited the features of algorithm execution and graph data, leading to suboptimal disk I/O performance. We propose a new out-of-core graph processing system, GraphSD, that greatly reduces the disk I/O overheads by simultaneously capture the state and dependency of graph data during computation. GraphSD proposes a state and dependency-aware update strategy that supports both state-aware I/O scheduling and cross-iteration vertex update to reduce the unnecessary disk I/O. The extensive evaluation shows that GraphSD can significantly outperform state-of-art out-of-core graph processing systems. And that's it. Thank you for listening.